Hello everyone, thanks for joining me today. My name is Arni Birgisson, and today I'm going to be talking about game backends and containerization. Now, I'm a developer advocate at AWS, focusing specifically on game tech, and I've been with AWS for coming up on 4 years now. First as a solutions architect, working with games companies, studios, and publishers, and prior to AWS, I led an infrastructure team for a game studio called Plain Vanilla Games. Now, in today's session, I'm going to be focusing on game backends and containers. But I'll start a little bit by telling you about AWS and game tech and the services that game tech provides and the global infrastructure that powers AWS. Then we're going to look into why you should be considering to use containers, what options you have for running containers on top of AWS, and what are some of the best practices that if you are building containers and deploying game servers with containers. Containers have a lot of benefits, so let's look at which ones of them are applicable and how they fit with game backends. Now, when you're deploying backends and servers for a global audience, it's important to have the ability to deploy infrastructure globally, because you want to be able to be close to the users and the players wherever they are in the world and wherever they want to play. AWS has the largest global infrastructure footprint with 24 geographical regions and 3 additional regions having been announced on the way as well, Indonesia, Japan, and Spain. Now, within these 24 geographical regions, we have 77 availability zones, and each one of those has at least one or more data centers, and which are isolated from any other availability zone. Now, there are 9 more availability zones planned also, and this infrastructure allows our customers and our users to create systems that are reliable and fault tolerant, as these availability zones are designed to withstand outages and be independent from each other. Now, we also have 97 different direct connect locations where you can connect your offices and data centers directly into your AWS Virtual Private Cloud, or VPC, and over 220 points of presence around the world where we have our edge services, including CloudFront, the CDN or Content Distribution Network, regional caches, and the Route 53 DNS service. Now, for a game that has players distributed all around the world, it's essential to be able to deploy game servers in regions that are close to them. And so, allowing them to establish low latency connections directly to the game servers that they play on. And all in all, this gives our customers the ability to operate production games and backends and databases that are more highly available and more fault tolerant and scalable than would be possible with a single data center. There's a number of studios that rely on AWS and game tech, and whether you are a big multinational studio or you're a small studio with just a handful of developers, you have access to the same platform, the same global infrastructure, the regions, all the availability zones, and the same services on AWS as Epic Games uses to run Fortnite and Rovio uses to run Angry Birds. And whether you're a team of 1 or 1,000, there's really only one thing that matters, and that's making a game that players want to play. And that's where we can help. AWS Game Tech provides robust and scalable technology solutions for every stage in the game's lifecycle, regardless of the studio size. And whether you're looking for source control or asset storage, managed game services, or if you want to utilize core AWS services, instances, storage, databases, networking, our focus is to be the most customer-obsessed company in the games industry. Now, one of the core services that Game Tech offers is Amazon Gamelift. It allows you to deploy and operate and scale dedicated servers for session-based multiplayer games, leveraging the power of AWS. And Gamelift is a fully managed solution. It offers low cost by leveraging all of the capabilities in the AWS cloud. Low latency and high availability by supporting 15 regions around the world, with more coming on the way, and flexibility to onboard different workloads at your own pace. With Amazon Gamelift, you don't need to do capacity planning. Instead of always running at peak capacity, as it's done in traditional IT provisioning, Gamelift will automatically scale based on rules that you create. So rules that are based on the number of game sessions that are running, the number of player slots that are available, or how long people are waiting to connect. So Gamelift has the knowledge of that it's running game servers. It's not just measuring plain CPU usage or that kind of load. And Gamelift is highly available. If one availability zone in a region becomes unavailable, new servers automatically spin up in a different availability zone based on the scaling rules. Gamelift also has automatic cross-region failovers, and players are placed in the best region based on their latency. And so if no sessions are available in a specific region, then players in that region would automatically be routed to a different region, which has the next best latency until the original one recovers. This in all brings significant cost savings, and you're always matching the amount of resources that you run to the demand from players. And last but not least, Gamelift Fleet IQ helps you utilize easy-to-spot instances, the excess capacity that's available in AWS data centers around the world at a significant discount of up to 90%. Now, to have a little bit of a closer look into how Gamelift works, essentially you have your game clients and they want to connect and be connected to other players on game servers. Now the game clients will interact with your game services or your game backend services, which in turn communicate with the AWS Gamelift service. The Gamelift service is composed of a few different parts. The first one is an optional matchmaking service, which is called FlexMatch. FlexMatch will form player matches. It'll find the right group of people to play together based on a set of rules that you provide. And when a group of players has been found and they've been matched up, these players are placed into a queue. And from that queue, they'll be routed to the best place for them to play together. Now, this is going to be one of the fleets that you are running. And these fleets host your game server builds on game server instances, which scale up and down based on player demand. So based on how many sessions are available and how many sessions are needed. The end result is that your players are matched into games by either your own FlexMatch or your own matchmaking system or FlexMatch. And then these matches get sent into the queues and from there placed into the best region. In this example here, they're placed in the EU Central 1 region, which gives the best average latency for the group. And what does a typical backend for a game then look like? So the Gamelift is one way of doing that, but typically you can sort of draw a line between certain components in a game. And of course, this depends heavily on the type of game that you have, but you can draw a line between the game backend services and the kind of game backend core, so to speak, which provides all of the services that are auxiliary to the main active gameplay of playing the game, the driving of the car or slaying the dragon. So these are things like authentication and leaderboards. They're the matchmaking and in-game messaging and chat, session management, even analytics. Those services follow and have kind of a certain set of requirements to them. And then the other part is multiplayer game servers, which have a very different set of requirements. Now, the top category, the game backend services, they are typically provided through standard APIs, like REST APIs, or perhaps GraphQL or something like that. And these services are typically deployed into fewer locations, perhaps one or two main regions and fallback region, something like that. These services are also often stateless and backed by databases and caches and utilize load balancers and can easily be horizontally scaled and so on. The multiplayer game servers, they have very different requirements. Typically, you want to have very, very low latency for those because latency is, or players and games are often sensitive to latency. And therefore, they are deployed usually into many regions around the world to be as close to the players as possible. Now, these servers also often use custom protocols, UDP instead of TCP, and when users have been matched up as a group to play, they're going to be playing on a specific server, and they're going to be connecting directly to that server. So quite different. And so let's look a little bit into containers then, and the benefits that containers bring, and we'll try to map those back to the typical game backends. Containers, first of all, they bring portability. When you package software into a container, you are creating a package that includes all of the necessary building blocks to run that software. Any libraries that are needed, specific versions of those libraries, any frameworks, and so on. And this creates a layer of separation from the host where the container will run, which now only needs to be able to run containers, but it doesn't need to know the specifics of your container or have anything kind of installed specifically for that container. So they're very portable. Containers are also lightweight. They're not full virtual machines, but rather they're isolated processes that are running on top of a shared kernel. And that means that starting a container is very quick. There's no boot up needed or anything like that. It's much closer to starting an application on a server. And since they're portable and they're lightweight, they're a great way to standardize deployments. And when you package your software into a standardized container image, and then you ship that image through your testing and QA and staging and production environments, you gain confidence in knowing that what you built on your laptop works the same way as it does in the testing environment, and in the same way as it does in the QA environment, and so on, all the way to production. And that brings us reproducibility. No more, well, it works on my machine. Now, I mentioned these benefits, the portability, being lightweight, standardizing deployments, reproducibility, but these abilities, they allow for fast deployments and horizontal scaling with high confidence and reliability. But how does that map to the requirements of the game backends? The first category, the game backend services, is relatively straightforward. These services fit quite well into the best practices for containerization. Game services can be stateless, shifting the state over to databases and caches, and therefore they can use load balancers, and they can be easily horizontally scaled, matching the demands from the players to the resources that you're running. The multiplayer game servers, they have been much slower to move towards that, and here's some of the reasons why. First of all, game server builds can be quite large, and large containers are a little bit harder to move around. They're also not stateless. Typically, the game server or the multiplayer game server contains a lot of state about the progress of the game, what's happening in the game, who has what, where is everybody? Excuse me. So that makes them much harder to scale, and especially when you're scaling down, because as the players have a direct connection to a specific server that they're playing on, you need to make sure that this game server stays available until the game is finished before making decisions to scale down. Now, here's an overview of the container services that are available at AWS. At the top, there are the service discovery features, Cloud Map and AWS App Mesh. Then we have the management layer, which includes deployment, scheduling, scaling, and management of containerized applications. Then and in that layer, we have the Elastic Container Service, ECS, and the Amazon Elastic Kubernetes Service, EKS. Both ECS and EKS support hosting the containers on EC2 instances, the worker nodes, or using AWS Fargate for a serverless option. And the Elastic Container Registry, ECR, is where you store all of the Docker images, all the versions, and all the different services that you have. And these are then used by whichever option you choose for both the management and the hosting. You're also free to use, of course, other image registries if you prefer. If we look at this individually, Amazon ECS is a fully managed container orchestration platform. It operationalizes your container workload at a very high scale without having you install any software. And ECS's control plane is a multi-tenant service, which can spin up large numbers of clusters and services and tasks underneath. Scheduling and orchestration are key components of ECS, and the cluster manager and the placement engine play specific roles to help accomplish these. Cluster manager manages health of the instances within the cluster, and you can set up an auto-scaling group and register your instances with the cluster. And ECS is aware of the capacity that you require for the containers that you want to run. Placement engines, on the other hand, enable much more advanced techniques for how you want to place your tasks onto the EC2 instances. For example, if you have certain tasks that you want to land on certain instance types, or if you desire super efficient bin packing for better economics, the placement engine allows you to do that. Now, if we look at EKS, the Amazon Elastic Kubernetes service, this makes it easy to deploy and manage and scale containerized applications using Kubernetes on AWS. Now, with Amazon EKS, AWS manages the Kubernetes control plane, and customers still run the worker nodes in their own accounts. With EKS, the complexity of standing up the infrastructure is simplified. Instead of running the Kubernetes control plane in your account, including the master nodes and the etcd nodes and all of the components that you require, you connect to a managed Kubernetes endpoint in the AWS cloud. And this endpoint abstracts the complexity of the control plane, and your worker nodes check into this endpoint too. Now, EKS runs upstream Kubernetes and is a certified Kubernetes conformant, so you can leverage all of the benefits of open source tooling from the community, and you can easily migrate any standard Kubernetes applications to EKS. That also means that you use regular Kubernetes tools like kubectl or kubectl to interact with this endpoint and with EKS. Now, our customer, Peak Games, that are creators of the popular puzzle games Toy Blast and Toon Blast, they shared with us how they traveled when they were on their learning path and their journey towards using containers. They started out trying a few different container orchestration platforms, Nomad, OpenStack, Swarm, and more, and eventually they decided to go with Kubernetes. Now, level 2 in their journey was to take Kubernetes the hard way, deploying every individual component to machines, configuring a cluster by hand. So while that helped them learn the components and the possibilities, they quickly moved to a more automated approach, trying out KOps or COPS and kubeadm and other tools to help with the deployment. They finally ended up using Amazon EKS to deploy their Kubernetes clusters. And as their senior DevOps engineer, Christian said, since EKS takes care of operating the masters, it was a very low effort way for them to set up the clusters and allow them to quickly spin up new clusters and try out changes. Now, Huge Games also has a similar story. With EKS helping to lower the overhead of system maintenance, this means that the team is able to dedicate more resources to what they do best, creating great games. AWS Fargate is a serverless compute engine for containers that works with both Amazon ECS and Amazon EKS. Fargate makes it easy for you to focus on building your applications and removes the need to provision or manage servers, and really just letting you specify and paying for the resources per application, improving the security through application isolation by design. Now, with Fargate, you don't have to choose instance types or scale the capacity of the cluster that is running the containers. You simply specify the amount of CPU power and memory that you need, and you only pay for the resources that are required to run your containers. With Fargate, there's no over-provisioning, there's no paying for servers that are sitting idle and have no containers on them. As Amazon's CTO, Dr. Werner Vogels, described it, you should be able to write your code and have it run without having to worry about configuring complex management tools. And this is the vision behind AWS Fargate. Now, if we think about game servers on AWS Fargate, they can be a great choice for your game backend if you need the ability to scale up and down quickly to match varying demands. And they can also be a great fit for lightweight backends, which do not require a lot of resources, as you can launch very small containers and even use multiple containers within each task. Of course, by using AWS Fargate, you don't need to worry about setting up the underlying hosts, including patching and updating. You simply launch the containers with the resources that they need, and Fargate takes care of the rest. Now, to get you started on this journey, we have an example solution on GitHub, which shows you how to scale a fleet of game servers on AWS Fargate and ECS, the Elastic Container Service. And the example also includes a serverless backend to route players to the game sessions and a sample client and server to try it out. The example solution's architecture looks like this. So you have clients on the far left side, which authenticate against Amazon Cognito. The client interacts with a serverless backend using Amazon API Gateway and signs the requests with the credentials that they got from Cognito when they authenticated. The API Gateway routes authenticated requests to an AWS Lambda function to request game session. And this function is backed with a Redis server running on Elasticache for Redis. When a game session is found for the player, it's reserved, and the player gets information about the IP address and the port of the container that is running on Fargate to connect to and play the game. There's a second Lambda function that takes care of scaling the environment, making sure to scale up when the amount of free sessions or available slots is too low. But scaling down is very simple because the containers are so lightweight and quick to start, they simply shut down automatically after having run a fixed number of games. The serverless backend also communicates with the game servers as they inform and report the status as they're available for sessions or have players playing on them and so on. And with this architecture, there are very few components that are constantly running and accruing costs. The Lambda functions, apart from the scaler function, only run when requests come in. And the amount of game servers that are running in the Fargate tasks reflect the usage and demand from players that are playing the game. And this means that you're only paying for resources that you need. So I encourage you to check out the repository. The link is there on the far left side on the bottom. And check out the step-by-step guide and deploy and try it out. Now, whichever solution you decide to use, whether it's ECS or EKS or Fargate, there are some best practices to follow when containerizing applications. And these are important if you want to reap the benefits of containerization, the portability, the agility, having reproducible outcomes and deployments. And so first of all, we're going to go through these. You should try to make containers small. This helps make deployments faster when you're scaling up, or if you need to redeploy or have a whole fleet of servers that needs to fetch a new version of the game server. You also want to keep only necessary software packages in the container image. There's no need for you to have additional software or tools in the image. If you need it later for debugging purposes, you can add it on the go. And you can also use multi-stage builds which essentially is a very neat way of achieving sort of the same. And we'll go through these individually. And obviously, shipping containers through all of your environments is very important as well. So let's have a look at these. So first of all, on the image size, and I'm sure you've seen examples like these a million times, but they're still worth mentioning because they're very important. When you build a Docker image, you have the starting image in the from line. But a simple change to using a smaller base image can give you a drastic difference. So here, for example, I have a simple main.go file that runs a web server, and both the source and the binary that is compiled are very, very small. Now, on the left side, my base image is the Golang 1.8 version, and if I use Docker to build an image from the left Docker file, it results in a 719 megabyte image. The one on the right, which is based on Alpine Linux, which is a smaller Linux distribution, results in a 306 megabyte one. So the resulting image size for this one line change is less than half of the original one. So quite significant. Now, the build cache, another important step here. When Docker builds images, it caches each step of the way in the build. So if you build the same image twice in a row, the steps that have been cached and haven't changed can be skipped, and these layers already exist on the node where you're building. When something's changing, file is added, removed, or changed, or a step in the process is changed, something in the Docker file changes, this breaks the cache, and you need to build from there. So to speed up development and CI/CD pipelines, it's important that steps that change more frequently or most frequently are late in the Docker file or lower down in the Docker file. So think source files and things that you're changing. And things that change least frequently, versions of dependencies, frameworks, libraries, operating systems, they are early in the Docker file. And so if we look at the example here, these two look quite similar. We have some Python server code here, which we're copying into the container, and then we install the requirements using pip. In the former example on the left side, since the code and requirements are copied in at the same time, this step breaks the cache if we change any code or any requirements. And that means that every time we build the Docker image, if anything has changed, we're going to have to be installing all of the requirements as well. Now, in the example on the right, we copy the requirements file in separately, and then we install the requirements, and last we copy the code in. If the requirements haven't changed in the meantime, all of the steps until copying the code in will be cached. And so there you see where I'm copying first the requirements file, installing the requirements, then I copy the rest of the code, and off we go. And so this significantly changes the build time for that particular image. Now, In the previous two examples, we've shown some ways of kind of mitigating behavior of Docker and tricks to keep things small and fast. But using multi-stage builds is an even better way of achieving these results. So in this case, the Docker file includes the building of two separate Docker images. The first one starts at the top, and we give that a name, builder. So you see from Golang Alpine as builder. So that image that we're going to create there is called builder. And this is based off of the Golang Alpine base image, which contains build tools that we need for building. Now, when we have built and compiled everything, then we create another Docker image, and that's where you see the second from line in the same Docker file. Now, this one is based off of Alpine, which is this very small Linux distribution, and it doesn't contain any of the build tools or the additional libraries and frameworks. Now, then we copy the compiled binary from the builder image into the final image. So the only thing that is in the final image, apart from this minimal Alpine operating system, is the executable. And this results in a 12 megabyte Docker image. And this compared to the 300 and 700 megabyte ones before. So it's very, very significant. This is also good for security because you don't have, in the final container that you're going to be running, you don't have a lot of different tools and libraries and frameworks and things around that you're not using. Now, one of the biggest benefits of using containers is the fact that you can be relatively sure that what you build and test is going to work the same way in multiple environments. So when you're working locally, you use your local Docker daemon on your workstation. And from there, you make sure that when you build container images, that they're built in a central location and then moved through the environments. For example, in this example here, we have a CI/CD environment that's responsible for building the container images when changes are made to the code repository. Now, if the images are then made available through the staging and production system, then we know that whatever we put through integration testing, whatever we put through QA and the staging environment is the same as what we deploy to the production environment. So what do we cover today? We've looked at the AWS infrastructure and AWS Game Tech and the services that are available from there. Then we looked at typical game backends, the split between the core backend services or the game backend services and the multiplayer game servers and how they're different. You heard about a couple of customer examples and then best practices when building container images. What to do next? Where do you go from here? If you're starting from scratch with AWS, I highly recommend that you begin with the Getting Started with Game Tech online tutorial. The course is both for business decision makers and technical roles who work in game development. It's a self-paced tutorial of about 90 minutes. And the course provides an overall introduction to AWS Game Tech services. You'll learn which workloads are supported by various AWS services and gain an understanding of the value that AWS brings to game developers. If you're a game developer, you can start by taking the compute path, or if you're a data engineer or analyst, you can take the analytics path. And of course, you can do both if you wear multiple hats. With that, I'd like to thank you for joining my session today. I hope you learned something new and that you're inspired to take the next step towards building better games. Check out the Game Tech website for more information and the Game Tech blog to learn more. Thank you so much. Bye-bye.